Assalamualaikum and hi everyone. My name is Muhammad Amzah bin Muhammad Noor and my matrix number is 212963. So today we would like to present the Computational Fluid Dynamics Project analysis of F1 car using CFD. So these are my group members, which are Alisa Nasuha, Nur Shafiqah, Nur Hamizah, Prasan and me myself. So I will begin with the introduction. So basically, since the 1950s, the automobile racing has been continuous presence, evolving from streamlined race cars to meticulously engineered vehicles optimized for downforce and faster cornering. In 1973, wings were introduced to enhance car stability. Thorough analysis of aerodynamics is crucial to achieve design goals, transitioning from wind tunnel testing to computational fluid dynamics CFD software for cost-effective assessment. Races take place on closed circuits with diverse turns, straight section and corners, allowing comprehensive testing of acceleration, cornering and braking capabilities. Formula racing represents the epitome of automotive technology, contributing significantly to powertrain suspension, safety features, and aerodynamics. This study focuses on the aerodynamic aspects of race cars using computational analysis techniques. The car's geometry is transformed into CAD format, followed by mesh generation and numerical solution of governing equation using ANSYS Fluent Solver. For the post-processing, with the CFD post provide visualization of pressure contours, velocity profiles and streamlines. Negative values in the pressure contours indicate pressure on how the below ambient level. CFD post also extracts the aggregate properties determining downforce and drag force exerted on the race car. Next we will move to the problem segment. So basically the continuous evolution of the automobile racing has led to the meticulously engineered race cars with aerodynamic exteriors that optimize downforce for the fastening cornering. To further enhance their performance, thorough analysis of the car's aerodynamic characteristic is essential. So traditionally, this analysis was conducted experimentally, so that using the wind tunnels, but the advent of the computational fluid dynamics CFD software has provided a cost-effective and efficient alternative in this study. We focus on the aerodynamic aspect of Formula One cars, aiming to investigate the impact of the different angles of attack on the vortex generation, drag and also downforce, if I'm not mistaken. That okay, by comparing designs based on the lift and drag coefficients, our objective is to identify the configuration that minimize drag while maximizing downforce. By addressing this problem, we seek to contribute the field's understanding of how CAD design and CFD analysis can be utilized to improve the aerodynamic performance of F1 cars.
Okay, I'm about to explain the modeling stage. The model was created using Autodesk Fusion 360. The model consists of chassis, wings, tires, side pods, diffuser, as well as the front and rear wings. The chassis is the main structural component of the car, providing support and protection to the driver. In this design, the chassis is represented by the streamlined body that resembles the overall shape of the F1 car. It includes the cockpit area of the driver's rear wing and front wing is also attached to this chassis of this car. The front wing is designed to generate downforce and direct the airflow around the tires. The rear wing, also known as the rear wings, is designed to generate downforce and helps to stabilize the car at high speeds. The next are the tires. Tires plays crucial role in aerodynamic, affecting the overall drag downforce characteristic. The next one is the side pods. and side air intakes which located at the side of the car. In F1 car, they helps direct air to cool down the engine and other components. In this design, the side pods are aerodynamic component located underneath the car. It helps to accelerate the air and create low pressure zone underneath the body of the car. In the design, the diffuser is not exactly visible, but the presence is amplified by the shape of the underbody. Lastly, the front and rear wheels are depicted as cylindrical structure attached to the chassis. For the modification part, we add some layers to the front wing to decrease the attack of angle.
Hi, my name is Alisa Nasuha binti Muhammad Hamidi and my matrix number is 212223. Okay, for our project assignment, I will explain two parts which are meshing and fluent CFD. So we start with meshing. So first, we created a box enclosure around the design car model as a fluid domain. So this way, we can simulate the air around the model. So you guys can see in the slide where the details of the enclosure and how the enclosure looks around the model. Next, to create the 3D grid on the box, we click on the Mesh at the Project Schematic window and the Meshing CFD Prep post will pop up. And at the details of the mesh window, we can see the element order was set to linear and the element size was set as default at 427.41 mm. And then we click the Generate tab to obtain the mesh result as shown in the slide. Okay, now in the Fluent CFD, we set the boundary condition was same for both design, where the boundary condition were divided into 4 parts, which are inlet, internal, outlet, and wall. So for the inlet, velocity specification method is magnitude, normal to boundary with reference frame of absolute, and the velocity magnitude was set to 20 meter per second and initial gauge at 0 Pascal, with turbulence specification method intensity and viscosity ratio, where the turbulence intensity is 0.5% and turbulence viscosity ratio is 2. So moving on to the outlet, the backflow reference frame was set to absolute with gauge pressure of 0 Pascal, pressure profile multiplier 1, backflow direction specification method normal to boundary, and backflow specification pressure specification is total pressure with turbulence intensity of 0.5% and turbulence viscosity ratio 2, which is same as the inlet just now. And then moving on to the wall, wall was sectioned to 2 parts, which are solid wall and wall. So for the wall solid motion, we use stationary wall, and for the wall, we use moving wall. Both are no-slip, and the roughness model was standard, where the roughness constant was 0.5. In the solver setting, a steady-state simulation was chosen as the temperature remained constant throughout the analysis, and the solver used was pressure-based, where focusing on the pressure field, and the velocity formulation was absolute, considering the magnitude and the direction of the vector, and the K omega model of turbulence has been applied in the simulation, and this model frequently used to depict the behavior of the turbulent flows. Okay, now moving on to solution method, we use coupled scheme for the pressure velocity coupling, where this scheme ensures that the pressure and the velocity fields are solved simultaneously, allowing for better accuracy and stability in the solution itself. And then for the spatial discretization, we change all of them to the second order, and we right click on the pseudo transient to open it, to let it on. And then for the convergence criteria used for the simulation were the convergence of residual and the convergence of the drag coefficient. The drag coefficient itself represents the drag force experienced by the object or the flow field, and its convergence indicates a stable and consistent drag force value. In the pseudo transient setting, the time steps method was set to automatic with a time scale factor of 1. The number of iterations chosen for our simulation was 20, where it indicates that the solver went through 20 cycles of calculation to reach its convergence and to stabilize the solution. Lastly, we use hybrid initialization in the initialization method.
For the results and discussion, this is the diagram results of our analysis in ANSYS for Model 1 and Model 2. Next, this is the result comparison of Model 1 and Model 2. Model 1 if the maximum pressure is 4.656 E plus O3 PA, while model 2 is 1.247 E plus O7 PA. From this result, we can conclude that model 2 has high pressure when we test it in CFD analysis. Model 2 has an additional wing that helps the F1 car to have a high pressure that generates high downforce at the front of the car, in addition to maintain greater speeds through turns and enhance overall handling. Downforce is needed to improve tire grip and stability. Increased downforce by the additional wing also helps to improve the F1 car stability and agility by reducing the tendency for it to lift off the ground or lose traction. For velocity of Model 1, the maximum velocity that can achieve is 4.374 E plus O2 meter per second, while Model 2 is 1.025 E plus O3 meter per second for 20 meter per second velocity inlet that we use. The additional wing in the Model 2 gives Model 2 the higher velocity, which is good for the F1 car to travel through the air with as little resistance or drag as possible. Also, the extra front wing can improve the car's acceleration by providing the additional traction to the front tires. Thus, the F1 car can accelerate more effectively, and then air resistance can be reduced too, so that the engine can produce more power to move the F1 car ahead.
Okay, this is the result of drag and lift coefficient for Model 1 and Model 2. To compare different model, we use the lift and drag coefficient. The lift coefficient, which is CR, represents the ability of the car to generate vertical lift or downforce, while the drag coefficient, which is CD, quantify the aerodynamic resistance. Based on the result of Model 1, the maximum drag coefficient is 0.65, while the maximum lift coefficient is 0.18 for Model 2. We add the additional front wing. The maximum drag coefficient is negative 0.085 and the maximum lift coefficient is 600,000. In CFD analysis using antithesis, the term negative and positive for the drag and lift coefficient are used to indicate the direction of this force relative to the reference axis or coordinate system. Thus, we can find the model that minimizes downforce, which is higher CL, while minimizing the drag, which is lower CD, is Model 2. When F1 cars is moving through the air, drag is resistance is encountered. On the other side, downforce is the force that pulls the car downward, which increase adhesions and allow faster cornering speed. As the result stated above, Model 2 is the better design for our F1 cars. In conclusion, CAD design and CFD analysis offer the effective method for enhancing the F1 car's aerodynamic performance. Engineers can find design configuration that's minimizing drag while maximizing the downforce, thus enhance the performance of the car on the racing course by investigating various angles of attack and their effect of vortex production, drag and downforce. From the result and discussion, Model 2 is the better F1 cars that maximizing downforce and minimizing the drag. It also has the higher velocity and pressure that can improve the performance of the F1 cars. That's all from us. Thank you.